All right, this is our extra credit chemistry project. Dustin, Brewer, Robyn and Priddy, and Jackie Raymond, and our molecule was C34H60O3.
So the first thing we wanted to figure out is our percent composition, and the molar mass of carbon is 12, and we were given 34 carbon, so 12 times 34 is 408, and then if you do that for hydrogen and oxygen, we got our totals here, and we added them up to 516. And then if we want the percentages of each carbon, then you'd have to do the 516 divided by the 408, which gives us 79.7%. And if you do it for the rest, you get all three of our percentages, which would be carbon is 79.07, hydrogen is 11.63, and oxygen is 9.3%. And then it says, if we were given 34.6 grams of our molecule, which is C34H60O3, how many moles can be produced with 34.6 grams? And so we did the mass on the bottom and then the moles on top. And so 34.6 divided by 516 is 0.0671 moles of our molecule. And then for number 3, we had to do the empirical formula. And we converted all of our percentages to mass, and it's just a straight conversion. And so for each one, like for carbon, we did the 79.07 divided by the mass of 1 mole of carbon, which is 12, gives us each percentage. You do that for all 3 of these, we figure out that our lowest one would be for our oxygen, and we got 0.581. And then if we divide all of them by 0.581, we will get what actually is inside our molecule. And we round the 11.34 to 11, the 20.017 to 20, and then the oxygen stays as 1. So our empirical formula would then be C11H20O.
So next we wanted to balance the equations, so we did the algebraic one, and we labeled each one as A, B, C, and D. And for this one, we had 34 carbons in the A section, so then we had 34A equals 1C. So we did that for the rest of them, and then we assigned each letter a number. We gave A for 1, and so when you plug that in and you enter it into these formulas, then you get all of these answers. But since this one wasn't a whole number, we had to multiply each one by 2 to get the final answers, and so that's how much is going to be for each reactant and product. And then for this one, we had to find the limiting reactant. So what we did was we found the moles of each one. So we know that we have 0.615 moles of oxygen. And when we did this equation, we knew that we needed 3.19 grams of oxygen. So we know that that one's a limited reactant. And so then we came over here and we generated how much we would make CO2 and H2O. So we entered in our limiting reactant and we divided it by 95 moles of oxygen, which is a ratio of 68 moles of CO2. And so then we did the same thing for H2O, and that's how we found out how much we generated of each one.
All right, and for our structural component of the our was it C36H60O3, we got this beast of a molecule. You can draw it in different ways, of course. This isn't the only way, which would be a resonant structure. For this, we have 96 sigma bonds, which would be just a single bond, all of these. And we got 5 pi bonds, 2 right here, 2 right here, and then the last one being right here. When it comes to the polarity of the bonds, this is kind of how we broke it down between the hydrogen and the carbon. They came out to be 0.4, which on the scale is barely polar. Oxygen carbon came out to be 1, which is polar. And then when carbon and carbon bind it to itself, like right here, we got 0, which would be not polar. And then lastly, for the hybridization of the carbons in specific, so we did these through these, since it's one ginormous long carbon chain, the hybridization would be sp3. This carbon and oxygen right here are sp, since there's only two adjacent molecules, or atoms, excuse me. And then sp because of the two adjacent atoms, sp2, and then sp for our last one. And then that should just about wrap up our structural component of our molecule.